scalar irradiance. Okay, that's cool. Now we get to the elastic scatter path function term. So we've got the radiance in the incident direction scattered from the incident to the final direction and integrated over all the incident directions. You know, that's just this term here, integrated over all the directions except the one we're interested in, which is the theta phi, but now we're integrating over theta phi as well. Well, L, the incident, doesn't depend on the final direction, so I can interchange the order of integrations. And so I'll integrate over the theta phi. This is over theta phi, this is over the primed. So now I'll integrate over the primed and then the integral over the unprimed part here. So I pull this guy out. So what's the volume scattering function for a given incident direction integrated over all other directions? What's that? Just the total scattering coefficient. Oh, that's cool. So this whole thing here is just by definition the scattering coefficient. And that doesn't depend on direction, so that B can come out. And now I've got an integral over the incident direction here over all directions. Well, once again, integral of radiance over all directions, that's just scalar irradiance. That's cool. And we're ignoring the source term here. Okay, so we back up, collect all these pieces. We have the left side of the equation became this, the beam attenuation term became that, the integral over the volume scattering function became that, but C is A plus B. So this is really minus A times E naught minus B times E naught plus B times E naught. So the scattering term goes out. And you take the result, you can solve for the absorption coefficient is the depth derivative of ED minus EU divided by E0. And that's Gerson's law, ignoring inelastic scattering. So that was like the masterpiece of his book, was to come up with this. So look what you can do. You can measure 3 irradiances and come up with an IOP. So this is what's called an explicit inversion of the light field to get an IOP. Explicit means you've got a particular little equation, you plug in the numbers and out comes what you want. So that's Gerson's law. Now what happens is if you have, let's say you're at 440 nanometers and Raman scattering's not too big and there's no chlorophyll fluorescence and there's so forth, this will work. If you go out to 685 nanometers and you measure these things and plug them in, you get some horrible thing like negative absorption or something because you've ignored the fluorescence terms out there, which can be included, but then there's more stuff you have to measure. And Ken has a paper where he made these measurements and used it to get absorption, and lo and behold, it works. Okay, it's 10 till, well, let's see, here's just another comment. If I have this term here, which is really minus A times E0, when I'm running an ecosystem model and I want to heat water or grow phytoplankton, well, in this case, I'm going to heat water. So T is temperature. So the rate of change of temperature with respect to time. Well, that's determined by how much light is in the water, scalar irradiance, times how much of that light is being absorbed by the water. And then there's a couple of factors out here that turn this into the right units. C sub V is the specific heat of seawater, which is like 3,900 joules per kilogram of water per degree C, and rho is the density of water, which is roughly 1,000 kilograms per cubic meter. And this comes from the first law of thermodynamics. Dig out your freshman physics book and you'll see how that works. So I can take the absorption coefficient times the scalar irradiance and say, oh, well, really, that's just the depth derivative of ED minus EU. So these are constants, I know those. So in ecosystem models, what they usually do is they have a model for ED, which comes from, guess where, our model for KD, which we talked about the other day, and then they put in the irradiance onto the sea surface, ED. They use the model for K. They get ED as a function of depth, and then they say, well, ED is like 100 times bigger than EU, so let's just drop the EU term. And that's how they compute the heating by the water in these big global ecosystem models. So it's a quick calculation. You can argue that, oh, well, you should have used EU, so you're off by 2%. And the answer is, well, who cares about 2%? We're off by a factor of 5 and other stuff. So that's how Gerson's law gets used for that. And there are other approximate analytic solutions. You know, Gerson's law is, if you wish, an exact solution if you ignore inelastic scattering. There's a number of approximate analytic solutions. Analytic meaning you can work them out with a pencil and paper. There's one I'll just very quickly outline in 5 minutes called the successive order of scattering solution, which leads to a thing called the single scattering approximation, which leads to a thing called the quasi-single scattering approximation. And we're not going to go through that, but here's basically the way it works. You assume the water is homogeneous, no internal sources, sea surface level, sun is a point source in the black sky, and the water's infinitely deep. Then you go through and say, well, okay, here's my RTE, and I've now written this in terms of optical depth, where the optical depth d zeta is beam C times the geometric depth. So 1 over meters times meters, non-dimensional. And we've assumed that the IOPs are independent of depth. So anyway, what you do, here's our equation. We write the radiance as unscattered radiance plus radiance that's been scattered once plus radiance that's been scattered twice, and so on. And those are weighted by the albedo of single scattering. Remember, it's equal to omega naught is B over C. So anytime there's a scattering, this is the probability that the photon's going to survive. So after one scattering, if omega naught's 0.8, 80% of those guys will survive. After 2 scatterings, it would be 0.8 times 0.8, or 64% will still be around. Well, very briefly, you take this, you stick it into this equation here, you get this, then you group the terms in powers of omega naught, and you say, well, suppose omega naught was 0. Then all of this stuff has to equal 0, which means this term has to be 0. Well, that gives us Beer's law. And if omega naught's not 0, we already know this is 0, and this is arbitrary, so the only way this whole thing can total to 0 is that each one of these things in brackets has to equal 0. Okay, so that gives you a sequence of equations that you can solve. And what you do is you solve the first equation, Beer's law, you take that and you stick it in here. And notice, because your RTE has the scattering term multiplied by omega naught, this is B over C, and I've written the phase function here, everything in here gets multiplied by an extra factor of the albedo of single scattering. So I end up with the equation for the first order scattering term involves the solution for the unscattered term being scattered. So I solve this, I stick it in here, and I get L1. Then the equation for L2 involves the light that's been scattered once being scattered the second time. And you work your way down, and you can actually go through that, and you get solutions that, here's examples here, comparing the single scattering approximation in red with Hydrolight's exact solutions in blue for small omega naught, a little bit bigger, bigger, and bigger. So you can see if the optical depth is really small, say less than 1, these equations work. Or if the omega naught is really small, the approximation works pretty well. But it doesn't work for big depths and big omega naughts. But then there's a second trick you can use called the quasi-single scattering approximation. That's another hour of derivation, but there's a page on the web book. And here you see, for example, remote sensing reflectance computed by the single scattering approximation. It works fine over here where water absorption is very high, so omega naught is small. And then here's the exact hydrolite in this quasi-single scattering approximation. Does pretty darn good. And it's a nice little thing you can work out or, write down with a pencil and paper. In the days of CZCS, when they didn't really have the computers, atmospheric correction was done using this analytical formula for the quasi-single scattering approximation. And it was all cooked up by Howard Gordon. So there's no time to go into that. You don't want to see the math anyway. Once upon a time, I threw the dart at the globe and it hit East Greenland. So I figured, well, I should go kayaking there. So here's Greenland and here's Iceland. This was the kind of area of East Greenland that's as close as you can get to Iceland. Now, all the people live over on the west coast. And this distance from here to here is the same distance as from the tip of Baja, Mexico to the Canadian border. And there's 3,000 people living there. There's a little blob of people here, and there's another little blob right up here, and there's a little blob here, and that's it. So you've got like I don't know what that is, 3,000 kilometers or something with 3,000 people. It's pretty unpopulated, but it's great sea kayaking. And that's kind of what the country looks like. All I can say is you need to go there and check it out. There's a little village, kind of has a dirt airstrip. So we flew into there from Reykjavik and we kayaked up to this little about, 120 kilometers or something, to a little village called Sørmilagak, which means beautiful ice fjord, and you fly into Kulasuk, which means bird's breast. And anyway, so we kayaked from Kulasuk up to Sørmilagak, and it was so mind-blowing that I went back a few years later and started in Sørmilagak and kayaked back to Kulasuk, so I'd see it in the other direction. And yeah, there were some big storms. We were pinned down for 3 days, and like 100-mile-an-hour winds destroyed all of the tents. I mean, it was epic, but that's why you go there, is to experience those things. Okay, so we can now go experience lunch. That's it.
What you're doing this afternoon is you guys are going to be working